Good afternoon. How is everyone doing today?
Hello, good.
Good. All right. Okay, so today's lab is about fluids. So different lectures may go about the pace differently, but usually fluids will be talked about later in the semester. 1510 is usually the last topic or the second to last topic. So most likely you haven't covered fluids in the lecture. So we'll spend a little bit of time to talk about the definition for specific gravity of any object and also Archimedes principle. So what we're trying to measure today is the specific gravity of different kind of objects. That's more dense than water, or object less dense than water, and also liquid. So let's start with the definition for specific gravity, and we will also go over our pre-lecture while we're talking about that. The specific gravity is simply a ratio. Use the density of the object divided by the density of the water, and that's give you a number, right? So if this object is 8 times more dense than water, then you use the density of the object divided by density of water, you get simply a ratio of 8. That's it. That's the specific gravity. So let's take a look at our pre-lab. First question is asking us to calculate the specific gravity of brass. All right, so we need to know the density of the brass. So how do we calculate density if we're given mass and volume? How do we get density from mass and volume? What do you think?
You divide them?
Very good. We use the mass of the brass divided by the volume of the brass. So if you're giving the same material, more volume you have, the more mass you're going to have, right? Because the density will be the same. So you can cut out a small chunk of brass, or you can use a big chunk of brass. The density that you measured will be the same, right? You use small mass divided by a small volume versus if you a big mass over a big volume, it's going to give you the same density because it is the same material. So for this particular block, it has this much mass. So we're going to use SI units. So I'm going to convert the grams to kilograms. It has a volume of this much. So you will be able to find its density. And the specific gravity is simply the density of brass divided by the density of water. The density of water is 1,000 kilograms per meter cube. So that's something you can look up for the density of the water. And we'll simply just compare everything to water, and you can have this ratio, a unitness quantity that is a specific gravity. So we're going to measure specific gravity. And the second, what we do in the lab actually relies on something called Archimedes principle. Archimedes is a Greek mathematician. So the common story of how he discovered the Archimedes principle, which is a way to measure the density of an object, is when he was thinking about this question in the bathtub. So what happens? What happens when you, what do you notice? When people sit in the bathtub, what happens to the water level?
It rises.
It rises, right? So whatever volume of an object, in this case, is the volume of a person, immerse themselves in the water, then the water has to make space for the object. So if you have this much of a volume, put in the water has to make that much space. So where would the water go? The water has to go up, right? In the case of rises, because it's trying to make space. Now, if you have a full tub, the water will spill, will go over. So in whichever case, its water has been displaced. We call it displaced, meaning that this volume, which was occupied by water, now is being displaced so that the other object could come into the water to replace that space. So you can see that the water has been displaced has the same volume as the object you immerse in water, right? So if it's 25 meters cube, then the water go elsewhere is exactly 25 meters cube of water that's been displaced. So Archimedes' principle is what he discovered is, okay, you know, this much liquid is being displaced and I can weigh this liquid. The weight of this liquid that's been displaced is exactly how much force is acting on the immersed object. And we call that the buoyant force. That is a force pointing upward, try to support the object. We know that if any object in the liquid will feel such an upward force, right? Try to have a buoyant force. Now, for an object that's less dense than water, that force is enough to balance its gravity. So the object simply stay afloat, right? But if you have an object that's much denser than water, then yeah, you still feel that upward force, but that force is not going to be enough to balance the gravity. So the object still sinks to the bottom. Okay, but regardless what kind of object you have, more dense than water or less dense than water, when you put it in water, it's going to feel that upward force. So if this is my water, and I put an object in it, put a rock in it, it's going to feel this buoyant force upward. But at the same time, it's going to have its own gravity, right? So depending on the density of this object, it might be able to stay afloat, or maybe you will have to sink to the bottom. So the Archimedes principle is saying the buoyant force is equal to the weight of the water that is being displaced. Okay. So we are going to take advantage of this principle to help us measure the specific gravity of the object. So really just we're trying to measure the density of the object. Okay, so how are we going to do this experiment? Let's take a look at a derivation here. So specific gravity is the ratio of these two densities. We have talked about this. You can see that since they occupy the same volume, you can multiply this equation by volume G, and that did not change the equation, right? But if you use the sample density times the volume of the sample, you get the mass of the sample, whatever object you're looking at. So mass times G is the weight of the sample. On the denominator, if you use this much water times this much volume, and that's the weight of that water, times G, and that becomes the weight of the water. Weight of the water of how much water? Of the equal volume as the sample. That's water that's being displaced when you put it in water. So you can see that the specific gravity can be calculated by measuring the weight of the sample. Okay, we can easily measure the weight of the sample, right? Just by putting it on a scale, read the mass, multiply by G. But we also want to be able to measure the weight of the water that is being displaced, which is equal to the buoyant force when you immerse it in water, according to the Archimedes principle. So we're not going to be able to measure it. So you might wonder, okay, can you just fill the container with water that all the way up and then let it spill? So whatever we spill, and then we measure that spilled water. That works. But if you measure this directly, it's going to get really messy and it may not be very accurate because you have to make it exactly full, right? No more, no less, and then spill it over during your transportation of collect what the water has been spilled and weight that you introduce a lot of error. So it's not going to be easy to measure directly. That's why we want to measure the buoyant force. And that's not easy to measure either, right? So, but alternatively, you're thinking, well, if you weigh it first in air, and you weigh it again when it's supported by water, it's going to, you are going to read a less value because you have a buoyant force acting on the object. So the difference in weight will be the buoyant force, right? So if you measure it in air, it says 10 pounds. If you measure it in water, it says 5 pounds. Well, that just means that 10 minus 5, the 5 pounds difference is how much the water is supporting the object. That's the buoyant force. So we can measure that quite easily. And that's what we are going to do in this lab is we are looking at the difference of the weight as a way to measure the buoyant force. So the specific gravity now becomes simply measure the weight 2 times, once in air, once in water, and then use W divided by W minus W naught. You can find the specific gravity. And that's that. So let's take a quick look at our pre-lecture. So I just went through how we derived this equation, right? And you want to now calculate the specific gravity. The rest is really easy. And this is exactly how we're going to do in the lab. We're going to read the mass in the scale. Okay, so find the specific gravity of this marble. You want to use the weight in air divided by the weight in air versus minus the weight in water. The weight in air is 7.2 grams, right? So that's 7.2 times 10 to the negative 3 kilograms in mass. And how do we get the weight from the mass? Still need to multiply that by G, which is 9.8 meters per second squared. So that gives you the weight. The weight in water is the same, 7.2. This is still going to be the weight in air minus its weight in water. So 4.5 grams. So convert that to kilograms, multiplied by G, and you get that. But you can see that in terms of the calculation, it can be much more simplified because you see that they all have the same G, they all have the same grams units, and you all convert it to kilograms from grams. So you could have simplified this directly, saying, I'm just going to use the mass in its grams unit, divided the mass in the grams unit, and that's going to give me my specific gravity. So that's what you can do in your lab as well, okay, because it is in grams, this is in grams, and G can cancel out. So you can just take this number as it is and do your calculation. It will be fairly straightforward and then much faster than if you had gone through all of those conversions.
Professor?
Yeah?
Are we supposed to keep that in grams?
Yes, keep it in grams, but you can see that it cancels, give you a specific gravity, which has its unitless quantity. So it doesn't really matter if you keep it as grams or if you wanted to convert it.
Oh, okay. Okay, thank you.
Sure. Okay, so let's go back to our lab, take a look at what we're going to do next. Before part A, so part A, they're trying to measure a variety of different objects. All of them are dense, more dense than water. Before that, they did a preliminary analysis where they're trying to verify Archimedes' principle. So they're trying to see if it is indeed the Boeing force is equal to the weight of the water. So they calculate they do this by, okay, the Boeing force simply by weighing the object in air and in water, the difference of that is the Boeing force that we can measure. And the water that's being displaced can be calculated using the water density and the volume of the object times G. So they measure this and they calculate this, and you can do this to show that whether these two are indeed equal or not. So we can take a look at our video. So let's go to our video. Okay, so they used this block, and they're saying we're going to determine the volume in two ways. Actually, you don't have to do it two ways. Simply, this is a cube, right, a long, and so you simply measure the length, the width, and the height, and multiply them together, you get the volume. They also put it in water and see how much the water level rises. They read the volume again. You don't have to do it two ways. Simply, you just do it using the formula L times width times height. So you see all of these different heights. For example, this measurement is for the length, for the height of the object is 77.5 millimeters plus or minus 0.1 millimeters. Okay, so 77.5, that's the height. Earlier they measured the length and the width, somewhere around 19 millimeters. So multiply them together, you get the volume of the block. And the volume of the block is going to be the same as the water that's being displaced. So you'll calculate the weight of the water by using the density of the water times the volume of the block times the little g. You can ignore this part. This is just still measuring the volume. We have already found the volume. So they had showed you the mass in air, which you can use to calculate the weight in air. And then now they're showing you the mass measured in water. So of course you cannot put the whole water cup on it. So you'll have to hold the water cup, but just have the object immersed in water so that the object is now being lifted up by the water. You're going to measure a smaller mass now. So this is using these data, you will be able to verify Archimedes' principle. The next part, part A, we're going to measure a variety of different objects. You probably already see they have brass, aluminum, plastics, and different kind of things, and cork and rocks. So you can choose 3 different objects of your own choice, but make sure you choose brass, because in the later part, they're going to refer to the data of the brass. So if you already recorded with the brass here, you don't have to read it again. So for part A, you will have to measure and record all of the masses of 3 different objects in air and in water. So let's look at the part A. that's the first object, graphite. The top one shows mass in air. The bottom one shows the mass in water. Okay, mass in air is around 6.9 grams. Mass in water, you can see it's much less. It's 2.9 grams. Okay, so you can record that along with the name of the solid object in your data sheet. So this is the aluminum. You cannot really see the 10 mark, so they told you need to add a 10. So the mass in air is 11 grams. Mass in water is simply 7.2 grams. And make sure they will go through a different object, the third object. The last one is brass that they will show you. So I make sure you do record the brass because they refer to that later. Now this one has a very blurry picture, so I will tell you what the mass is. The mass for brass in air is 34.4 grams. Okay, so maybe you can make out that picture. It's 34.4. The mass of the brass measured in water is around 30.4. Okay, so that is the last object for all the objects that's more dense than water. Okay, so let's let's go back to our data sheet and we take a look at where we are so far. So you can see with those data, you're able to fill in these table, right? Make sure one of them is the brass. In air is a little harder to read, is 34.4, and water is 30.4. You can calculate the weight again, and then use this equation to calculate specific gravity. But like I said, when you do the specific gravity, actually the little g cancels. So you could simply use, for example, S for the brass. When you do the calculation, you can simply use 34.4 divided by 34.4 minus 30.4. So right away you get a number. You can put that number in here, okay? You don't have to worry about converting it to weight first, because all of those eventually cancel out. Okay, so that's part A. Make sure you include your units, okay, whether it's grams or kilograms, and the weight should be in newtons. Yeah, so the weight would be the mass, so in kilos times 9.8. This will be in the unit of newtons. Okay, that's the weight. Actually, you don't even have to calculate it because, like I said, this calculation doesn't rely on getting this number first. So you can just show me the process, just leave it as that, and then do this calculation and give me the specific gravity. Okay. And then they will show the diameter and the length for the different objects, because this is a cylinder. So then they measure the diameter instead. Okay, so the volume, how do you measure volume of a cylinder? Volume of a cylinder is the surface area multiplied by the height L. Okay, so that's pi r squared times L is how you're going to calculate the volume. So later on in the video, they will show you the diameter of the different objects. The second part is, what if you wanted to measure something that's less dense than water, and the one we are using is a cork. So this is really funny because you can see that, well, this is the object you're really interested in measuring, but it needs a sinker, right? Because the object is less dense than water, you cannot make it fully immersed unless you have something to drag it down, right? So in order to be able to get the actual accurate buoyant force on the object, you need to be fully immersed. So the sinker is simply there to make the object go down into the water. But the weight you're measuring should not be dependent on the sinker. So you can see that for part B, very interesting. The buoyant force when the sample, which is this cork, is immersed in water is a difference between weight one and weight two. Weight one is when the sinker, well, sinker is always in water in both cases, just so that the sinker is not a factor. But the difference between these two scenarios is the cork is now in air and now the cork is in water, and you measure that weight difference. That difference will be how much force is supporting the cork from the water, right? The sinker is the same in both cases, so it's not going to matter. And you do the same thing by writing down the mass measured in air by itself. That's the weight that gives you the weight of the cork itself. And in air where the cork is outside, the sinker is in water, and then both of them are in water. So there you have 3 different weights, W, W1, and W2, and you can calculate the specific gravity. So let's take a look at our video for that particular part. Okay, here they're just showing you the dimensions of these different objects. This is the left-hand side is showing you the diameter. The right-hand side shows you the height or the length of it. And if you need to think about how do you read the scale, you can go back to lab 1 to be more familiar with it. And that's the different objects. Now, if you're interested, you could also do the rock. It's not a regular shape, so the volume of the rock cannot be determined by measuring the length, right? It's an irregular shape. So instead, they put rock in water and read how much water is being displaced. I think this is a good skill to learn how to read the volume correctly. So you can see that you want to be able to read where the lowest part of the surface of the water. So the water will intercept with the container. The two edge might be a little bit higher, and the middle, the middle is a little bit lower. So you want to read from the middle, but not from the edge. So this is how they measure the rock, but you don't have to do that. That's just for fun. Part B for solid that less than water. Okay, they went relatively quickly. Let's slow down just a little bit. Okay, so this is the mass of the cork. Okay, it's a little blurry, so you might have skipped that. It's very little mass. It's 2.1 grams. That's the mass of the cork. Okay, so this will give you the weight of the object in air. W1 is the cork is in air, but the sinker is in water. W2 is most of the object is immersed in water, and that's you can see it's like 18.4 is your W2. The last part is the liquid. Okay, all right. So you also want to measure the density of the liquid. So you might wonder, okay, what do we do now with liquid? You cannot put liquid in water because it's not so much about immerse something in water. It's itself is in liquid. So what do we do if we want to measure the specific gravity of the liquid? So we cannot put liquid in water, but instead we can put a solid object in the liquid versus in the water, and they will have different results. Using that, we're able to relate the density of the liquid to the density of the water. Okay, so this will rely on this little bit derivation. Let's take a look at that. So how do we find the liquid density? Well, let's multiply the equation by the same volume of the liquid times little g. So this one becomes the weight of the liquid, and the bottom becomes the weight of the water, which of the same volume. So how can I make sure I'm measuring the same volume? Well, if you immerse the same object into water and the same object into the liquid, you can make sure that what is being displaced is the same amount of volume, right? You displaced this much water, and the same object you put in alcohol, for example, you need to displace same amount of alcohol. So instead, this equation has translated into what have become a ratio of the Boyne force provided by either the liquid or the water. Okay, and Boyne force is simply measured by the weight difference. So you immerse the object in water first and then the liquid, twice. This weight difference gives you the Boyne force of the water provided. This weight difference gives you the Boyne force that the liquid provide. And this will be able to give you the result for specific gravity. Okay, so that's the little technique that they used to measure the specific gravity of alcohol. That's the liquid they choose to use. Okay, so let's take a look at their measurement. So they need to rely on one solid object to immerse it in liquid and water. The liquid they use right now, what they poured is the alcohol. And you can see they are not going to give you immerse the brass in water again, because the data has already been taken in part A. So you can record whatever data you had in part A and copy it over here. The new data is simply immersing brass in the alcohol. That's what they're doing. So if you still remembered our results, when you immerse that brass in water, that's 30.4, right? Now you immersed it in alcohol, this data give you 31.1. Okay. So it looks like when you immerse in water, you read a less value versus if you immerse it in alcohol. So what does that tell you? Does that tell you alcohol is more dense than water or less dense than water? What do you think?
More dense?
And why would that be? How can we relate that to this reading on the scale?
Because the weight of the object got lighter. Actually, let's say I had it backwards to less dense.
Okay, yes, the weight of the object got lighter in both water and in alcohol, but it got lighter even more in water. Very good, Edward. So which means that the water was able to provide even more Boyne force. That depends on the density of water is So is density of the water is a little bit more than the density of the alcohol. Very good. Thank you for Neil, who also contributed to this question. But it's really close, right? So the ratio of alcohol's density versus water density is pretty close. Now, eventually they measured that using a hydrometer. It's just simply a device that you can measure the density very directly. You can compare our measurement to what you would have read directly. So let's see what that will give us. Okay, so it's not very clear, but you can see that there were two scales. One read is 0.8, right? The bottom one is 0.85. And looks like the level, the water level is exactly in the middle, even though there is no numbers written, but it's exactly in the middle. So we will read the specific gravity of the alcohol using the hydrometer to be 0.825. So that's halfway between 0.8 and 0.85. Okay, so 0.825. You can verify if that is the same value as the one you measured using the Archimedes principle. So that's all. That concludes our lab. Let me bring back my slides.
That number that right there is that's like the rate, that's the decimal ratio for alcohol versus water.
Yeah, that's the hydrometer gives you the specific gravity directly. Like it's already designed in such a way that tell you what the ratio is. So what you just saw, this value, and you write it here. And you will calculate it, right? Specific gravity you calculate using this in the liquid. This is in water. So you do a calculation and then you compare it with this result to see if they match. Do you have any more questions regarding this lab about the 3 different parts? Part A is measured objects. They showed 4 different objects. You choose 3, but make sure you include brass. And part B is the cork, and part C is the alcohol. Any questions?
I had a question for part A. For the diameter of the first solid graphite, do we just choose any diameter that we want? Because it said it's the same for.
Oh, yes. I think that all of the different objects have the same diameter and length. Graphite and lucite, brass and aluminum. You can verify that by just looking at the different scale that they showed in measurement. But the last one they didn't say, right? They say it's the same as the other cylinders. So yeah, but all other cylinders are the same. So it doesn't really matter which one you choose.
Okay, thank you.
Okay, thank you for the question. There's another question in the chat that says, in part A, when we measure objects, do we convert millimeters to centimeters or meters, or do we just leave it in millimeters? That's a great question. So the question is, okay, we measure the length and the width, and then what do we do with it? We wanted to find the volume. And then we use the volume to find the weight. So if you want your final measurement to all be in newtons, then you will convert the millimeters to meters. Okay, so I would recommend you convert it all to meters so that all your calculation is give you the unit of the weight in newtons. So later on, you measure the weight by putting in a scale, and you have to convert that to kilograms, and then eventually the weight will be in meters. So if you convert everything, you can make sure everything will be consistent. Does that make sense? So part A, the preliminary, it's the preliminary when you verify Archimedes principle, you calculate the weight using the volume, and then that give you the measurement of the height, the width, and the length. Any other questions?
Are the numbers from the preliminary, are those the same numbers that we would be using, that we could actually use, or are they different in part A for aluminum?
Okay, sorry, I don't quite get your question. Can you say it again, please?
Okay, so in part A, you know, they had different objects, right? And
Yeah.
one of them was graphite, the other one was aluminum, and then you chose to use brass. So in the preliminary, it says that that's an aluminum block as well. So
Oh, yes.
is that the same block or is it different?
It's actually different. The preliminary used like a square block, and then in our actual measurement, part A, it's a cylinder. So it's different, different object.
Okay.
But the specific gravity in for aluminum should be the same. So, Giovanni, thank you for your reminder. I also want to remind everyone, our quiz 3 is today. This will be based on our previous 3 labs: circular, uniform circular motion, and we have the rotational dynamics, and also a static equilibrium. So those 3 labs is our quiz 3. Any other questions, everyone? I want to say, once you get a specific gravity by putting objects in water. You can also, since you are given the different diameter, you can also calculate the density directly by use the mass that you measure divided by its volume. So this is sort of a more theoretical method in part A, and where you use Archimedes principle is more of an experimental method. You could compare the results of your specific gravity for the same object. They should agree with each other. So this is more like a sort of a check table, just to check if your answer agrees with what the theoretical value is say. All right, any other questions? Okay. All right, if no more questions, I do see another message sent to me. I will respond. We will respond, communicate separately on that issue. Okay. And for the rest of you, have a good rest of the week, and I will see you next week. Bye, everyone.
Thank you, Professor.